Let's solve the following system of linear inequality. So here we have the absolute value of x minus 2 is greater than or equals to 5. We'll begin by using the definition of the absolute value. We know that absolute value is defined as absolute value of x will be equals to positive x if x is a positive number, and it's going to be negative x if x is a negative number. So using this definition, we get two cases. So case number 1 tells us that if x minus 2 is a positive number, then it follows that x minus 2 is going to be greater than or equals to 5. So let's solve this. So this gives us x greater than or equals to 7. Fine. Then if we take the second case, case number 2, the state says, what if x minus 2 is a negative number? In that case, we have negative of x minus 2. So that's going to be greater than or equals to 5. Or simply, we get negative x plus 2 greater than or equals to 5. We'll transpose 2 to the right-hand side. So that gives us negative x greater than or equals to 3. Here x has a coefficient of negative 1, but we want to make it positive. In order to do that, we'll have to multiply throughout by negative 1, but we have to be careful here. So when we multiply with a negative number, the sign of the inequality changes, meaning, we state it here, let's say if we have two numbers a and b, and a is greater than or equals to b, and we also have another number c which is less than 0, that means it's a negative number. Then if we multiply a with this negative number c and also b with the same negative number c, then the sign of the inequality changes. That means ac will become less than or equals to bc. So this is what we have applied here. Now that we have obtained the solution for x for both of the two cases, let's try to combine it. For this, we are going to sketch a number line. On the number line, we'll consider negative 3 and positive 7. Now x greater than or equals to 7, that means we have to consider all the values of x which is greater than 7. That means it's a part of the it's going to lie to the right of x equals to 7, and since x equals to 7 is also a part of the solution, here I've used a dot, and it extends all the way up to positive infinity. Then we have the second case which states that x must be less than or equals to 3. So we'll consider all the values of x less than negative 3. That means lying to the left of x equals to negative 3 and extending all the way up to negative 3, infinity. So here my negative 3 is also a part of the solution. So I've used a dot here. Now we want to express this number in an interval form which will become the solution set. So here we have our values going from negative infinity to negative 3. So here negative infinity by definition is unbounded, so we'll have to use a open interval, whereas negative 3 is a part of the solution, so we'll use a closed interval. So this is one solution obtained from case B, and we have another situation where x is greater than or equals to 7. So we'll have to consider that, or we have the solution going from 7 to positive infinity. So 7 is included, we'll use a closed interval. Infinity is unbounded, so we'll use an open interval. Now that means x must lie between this particular interval. So this is a solution to the given system of linear inequality.